Thank you, ACM, for having me. I have admired ACM for decades, going back to when I was in college. I've admired the organization and just everything that ACM has done. So I'm deeply and powerfully honored to be speaking at an ACM meeting. This is something I'm really excited about. So I'm going to start talking, and let's talk about Parallella, and let's talk about parallelism and embedded systems, and towards the end we'll have Q&A, and you'll ask questions. I'll answer what I can. I have a few parallels with me, and we'll dig into those. Starting off, Moore's Law is running out, and my clicker is not working. No, now it's working. Okay, Moore's Law is running out. And in this room of engineers and computer scientists and digital enthusiasts, you all know what Moore's Law is. Moore's Law is the observation that we will be able to double the number of transistors on a wafer of silicon every 18 months or so. And this is a graphical representation of Moore's Law. A more visual representation of Moore's Law is this photograph. All of the functionality in the devices at the top is embedded in the device at the bottom. That's Moore's Law. That's what happens when you double the number of transistors on a wafer of silicon every 18 months. So that's Moore's Law. But Moore's Law is running out, the party is almost over, and we as developers, designers, engineers, digital enthusiasts, we need to come up with another way or other ways to extract more performance from a wafer of silicon. One possible way is parallelism, and we might be able to explore that in a device called Parallella. And here's a Parallella. All right, Moore's Law is running out, and clickers are erratic. So I'm going to do this from the machine itself. Yeah. Well, there it is. There's the Parallella. Okay, that's a Parallella. Parallella is a single-board computer, roughly the size of a credit card, or a Raspberry Pi, or a BeagleBone Black, or an Arduino. Here's a Parallella in my hand. And this particular Parallella is inside of a 3D printed case. Pretty neat. You can take a look at it later. Again, Moore's Law is running out. We'll explore it through a device called Parallella, and we'll dig deeper into that. My company, Wisdom Group, my name is Ray Hightower. I run a software company called Wisdom Group, and my team and I together, we run the Chicago Ruby User Group and a couple of conferences, Windy City Rails in Chicago and Ruby Caribe in the Caribbean. We became interested in Parallella when we began working with a client that studies massively parallel systems. And by massively parallel, I mean systems that have 100,000 cores or 1,000,000 cores or more. And they're studying these systems, they're collecting a bunch of data on heat dissipation and power utilization and all of this, and they're putting it into a database. These are the types of supercomputers they're studying, Craze and IBM Blue Gene, and they're putting all this data on performance into this database. And they asked Wisdom Group to build web apps that would enable them to keep track of the data that they're collecting. The engineers, the scientists who are studying these massively parallel systems are some high-end PhD computer engineers, computer scientists. We don't understand everything that they're looking at. But we know enough to build web apps that enable them to get insight into their data. The metaphor I like to use is, it's as if they're medical researchers studying the deadliest diseases ever encountered by humans, and they asked Wisdom Group to build microscopes. So we build web apps to give them additional insight. So the more we understand about what they're looking at through these tools, through their microscopes, or through the web apps that we build for them, the better job that we can do for them. So we went out and began looking at Parallella because it's an inexpensive device, an 18-core device that we can use to study parallelism. And the Parallella, it's just a Linux computer. You've got an RJ45 Ethernet connection, you've got micro USB, micro HDMI, micro SD for your storage, where you would have a hard drive. No, here you store your OS and you store your data on a micro SD card. It's got 18 cores, 2 ARM cores, and 16 RISC cores. And I'll dig into ARM and RISC in a minute. All of you know, pretty much everyone in this room knows what ARM and RISC are. The 3D printed case that I showed you earlier, this is it. This was 3D printed by a team at West Point. Professor Suzanne Matthews and her team at West Point are teaching courses on parallelism to students at West Point, and they needed a case. So they came up with this 3D printable design. that you can download from Thingiverse. So if you want a case like this, you don't have to pay for it. The plans are free. You download it, and you need to pay money for the filament, of course, and the time on the 3D printer. You can print your own Parallella case. Exciting thing about this particular Parallella case is that it stacks together like Legos. So as you can see in the photograph, there are 1, 2, 3, 4 of them stacked together. So if you want to put together a Beowulf cluster of Parallellas, you can do that and have your cable management going on and have it, very neat. Because all of us as computer scientists and engineers, we like to keep our desks as neat as possible, right? So here's Parallella. I'm going to show you what it looks like when it's booting. And this is it. It's just a Linux computer. It's up, and it's got a, let me go back to this again. Are we starting? We should see yeah, there we go. We've got a terminal window that's coming up. So it's Linux. It runs a distribution of Linux called Mandelbrot, especially for Parallella. And you've got a web browser, you've got Firefox, you can run Chrome on it if you want it. So it's a normal computer, a normal Linux computer. But you want to do more than just, run it as a computer. You want to do some experiments with it. You want to dig into it and figure out how, what am I going to use this for? One of the most critical things you want to be aware of, and that you want to study if you're going to use this as an embedded device, is its power utilization. 2 reasons. The more wattage you're using, the less your batteries are going to last, and also the more money you're going to spend. With massively parallel systems, one of the things that the hardware engineers look at when they're studying the power utilization of massively parallel systems is they look at power utilization, and when they're looking at the budget, the amount of money that they're spending on electricity, they figure that 1 watt used over the course of a year is going to cost about $1. Or 1,000,000 watts used over the course of the year is going to be about $1 million. And in the case of the fastest computers on the planet, this is from top500.org. I have the top 3 here. The fastest computers on the planet are using millions of watts over the course of a year. Number 1 is using 17 million watts, 17.8 million watts, almost $18 million per year that you would need to spend if you had one of these running in your basement or wherever it is that you run your computers, right? Because watts are dollars. Cool thing about Parallella is that it's a very low power device, and I needed a way to convince myself that it was indeed low power. So I grabbed one of these. This is a charger that you might use for your cell phone. On one face is a photovoltaic cell, just a solar panel. Inside is a lithium-ion battery. You can buy these devices online for about 20 or 30 bucks a pop. And there are 2 USB outlets, one 1 amp USB outlet and one 2 amp USB outlet, each at 5 volts. And I took an old power cord. I'm in a room full of kindred spirits. So, in the back of my closet, got a box. You know how when you buy an electronic device and then after a while it gets old and obsolete, and you either give the device away or throw it away or it breaks or whatever, but you keep that power connector, because just in case, right? You might need it for something. So over the years, those things pile up. So I got a pile of those in a box, right? So I took one of those out. This is one of those times. I'm glad I saved it, right? This is one of those times. Took one of those out. Jerry rigged it with a USB cable, hooked it into the combination solar panel lithium-ion battery, and soldered them together. If you want details on which lines were soldered with which, that's on my blog at Hightower.com. And ta-da, it worked. So 5 volts, 1 amp powers the Parallella. So the math said that it worked. So I should have been convinced just by the math, but doing this is, is a cool way. As engineers, as scientists, we kind of need empirical evidence when we're working with something, right? We kind of need to know, need to see it happen. All right? Now, let's talk about hardware architecture and parallelism. Parallelism is not new. Parallelism has been around for a long time. This is Grace Hopper, and I won't read the whole quote to you, but the bottom line is, the idea behind parallelism is that instead of growing a bigger ox, we're going to take multiple oxen and hook them together, and that's how we're going to achieve more power. I should also say at this point that concurrency and parallelism are 2 different things. There's a great video about this by Rob Pike, one of the creators of the Go language, Google's Go language. Concurrency and parallelism are two different things. I didn't know this before I started working with Parallella. What I've discovered is that concurrency, you can achieve concurrency on a single processor system because it's almost an illusion. You know, say you've got your event loop in your operating system. Your event loop is looking at what's happening with your mouse, what's happening with your keyboard, what's happening with your disk drive, what's happening with all of your systems. And it's doing a task switch between all of those. In Windows, I think the quanta they used was 20 milliseconds. Every 20 milliseconds, it would task switch to something else, to another device, and run it for a little while. And so the single processor system was doing all of that. But to the human, it appears that things are happening concurrently. But with parallelism, you have processors that are actually running things at the same time. So there's the difference between concurrency and parallelism. Rob Pike in this YouTube video does a more in-depth job of explaining the difference between those. But they're actually two different things, and you can leverage each of them depending on what type of application you're writing and what it is you want to accomplish with your software. Talking about hardware architecture, we mentioned RISC and ARM earlier. RISC, as many of you already know, RISC is reduced instruction set computing. Bottom line, RISC is the 80-20 rule applied to computer architecture. Scientists and engineers, computer scientists and computer engineers have observed that 20% of our instructions are executed 80% of the time. Therefore, let's make those our most performant instructions. And let's build the rest of our instruction set on that. And that's what RISC is about. ARM is intellectual property created by a company in the UK called ARM Holdings. Acorn RISC Machine, Advanced RISC Machine. The exact definition of the letters in the acronym has evolved over time, but that's a company in the UK that sells intellectual property for RISC chips, and so those are ARMs. And on your Parallella, you have your 2 ARMs and your 16 RISC that's on the Epiphany trip. So let's take a look at these 16 RISC cores. You have 4 rows, 4 columns. Like good computer scientists, we start at 0. So row 0, 1, 2, 3, and column 0, 1, 2, 3 are what we have. So that's how you designate each of the cores. Let's run a program. We're going to run something called Hello and Epiphany. This is what Professor Matthews runs with her students in her parallel programming course at West Point. And every Epiphany program or every Parallella program has 2 components. There's a host component and an Epiphany component. Because your operating system is running on your host, your 2 ARMs, and all of your parallelism takes place on those Epiphany cores, and they communicate with each other. So let's take a look. This one is a real simple one. What's going on here? We're going to build it and run it. And yes, you do have GCC on this, so you're teaching this right on time, right? So as you can see, inside of the ordered pair, inside of the parentheses, you have row, column. And in this particular program, this is just a warm-up exercise. It's reaching out to each of the cores at random, and it's just saying hello from core and which core designation it is. Not a big deal. It's just like a stretching exercise before the real workout. So for a better workout, or to do something more interesting, let's take a look at prime numbers. Because as computer scientists, we need large primes, especially if we're doing something with encryption. And in this case, let's look for all the primes between 0 and 16 million. We'll do that in C. And here, isPrime is the most important function of this program. I'll zoom in on it a little bit closer. isPrime, this is it in C. And as you can see, we are starting at 3, iterating by 2, because you're only going to look at the odd numbers if you're looking for prime numbers, iterating by 2, and we're only going as high as the square root of the number we're investigating, because that's as far as you need to go. And that's the prime number algorithm we're going to use. Side note, I presented this at a conference once, and someone asked me afterwards, well, Ray, why didn't you use the sieve of Eratosthenes or Eratosthenes? How do I pronounce it? Eratosthenes? Eratosthenes. Eratosthenes? Okay. Ray, why didn't you use the sieve of Eratosthenes? because we're demonstrating parallelism, and that's what we're looking at right now. And I suppose we could look for or come up with a way to do the sieve of Eratosthenes in parallel, but then we'd have to explain that in addition to explaining everything else that we're doing. So this, yes, this is a brute force way to examine parallel numbers, and that's what we're doing. So are we doing the sieve of Eratosthenes? Well, first I need to learn to pronounce Eratosthenes, and then maybe we'll explore it. But for now, we're doing a brute force algorithm to find prime numbers. So here we go, and let's watch it execute. And what we're doing first is we're going to execute this algorithm in serial on the Parallella, because that's just going to be our benchmark. And inside of the program, we are also telling it to print out the number that we're investigating every 100,000. So every 100,000, it's just going to tell it, just to let us know that it's doing something. You know, just so we know what it's doing. There's your elapsed time. And it could run for a while, so I'm only going to let it run for, really less than 30 seconds. And it found, under 16 million, it found 1,031,130 primes. It did that in 237 seconds, just under 4 minutes. All right, so that's our benchmark. That's in serial on the Parallella, just employing the 2 ARM cores on the Parallella. Let's run the same program in Mac OS X on MacBook Pro, particularly this MacBook Pro that I have up in front of me. It's the same code, written in C. We're going to build it and run it on the Mac. So here we go. And we're going to make it. And we're off. And we can already see that it's running faster. It appears to run faster. This is in serial on a Mac, and you expect it to run faster because a Mac is a faster machine. Or it's a more expensive machine. Faster, it's a more expensive machine. We're going to find out if it's faster, right? So it found the same number of primes, 1,031,130 in 14.4 seconds. Now let's do something interesting. Let's look for primes on the Parallella. And in order to do that, we're going to have to modify our program slightly, because as we discussed before, you've got the 2 ARM cores, your 16 list cores. We have to modify the program so that the parallel portion is running on the 16 Epiphany cores. We have to split up the work. And you can see what's going on here. At the very top, we're doing an include in C. We're including eHal.h. That's the Epiphany hardware abstraction library that allows us to talk to those Epiphany cores. And we're looking at 500,000 values per core. And those of you who are really good at mathematics are saying, wait, 500,000 times 16, that's only 8 million. Well, again, we're only looking at the odd numbers, right? We're not looking at the even numbers, so we only have to look at half of them. So let's watch this run. And there we go. The ordered pair on the left inside of the parentheses is row and column for the core. The number of tests that we're running is in the next column. We see the number of primes that it has discovered so far, the current number under investigation, and the square root of that number, because you only go as high as the square root. And it's done, and it finished in 18.6 seconds. So here's the summary of our results. In serial on the Parallella, about 4 minutes. Serial on the Mac, about 14 seconds. Parallel on the Parallella, about 18 seconds. So ladies and gentlemen, we've got a $150 single board computer, about the size of a credit card. This thing right here, 150 bucks. Or $99 if you're like Jeff Biggis and you bought a headless version, right? 150 bucks. That is performing on the level of a $2,000 Mac. What? Well, I would share with everyone, you don't want to throw out your Macs because, excuse me, this is an example of what we call an embarrassingly parallel program, or an embarrassingly parallel problem or program. By embarrassingly parallel, we mean it readily lends itself to being split up into chunks so that you can divide the work amongst the many cores. And a problem like that is one in which the future result is not dependent on a previous result. A problem that might not be embarrassingly parallel is probably something, let me think of a simple problem that might not be embarrassingly parallel, probably the calculation of the Fibonacci sequence, because Fibonacci, you're looking at the previous two, right? So that's probably not easily parallelizable, but maybe someone has an algorithm for
There's a
that.
closed form solution. Yeah.
Oh, there is?
Yeah, you don't have to do the recurrence.
Oh, really? Okay, very good. Thank you. One of the advantages of being in a room with smart people is that when I say something stupid, someone will correct me, so thank you. So I appreciate that. And I'm going to want to ask you more about that, because I'd like to know more. I've looked at Fibonacci with memoization and some other things, so I'd like to look at it deeper, so thank you. So let's have a little bit of fun. Parallella is very good at calculating the Mandelbrot set. And we'll run that, and I'll let you take a look at it. It does that in a, let's see, is my clicker there? How are we doing? Okay, good. We're looking at the frame buffer on the Parallella, and don't worry about what you're not seeing here. These are just the commands where we're telling you to make and build and run. But in a few seconds, you're going to see the Mandelbrot set being calculated, and this is it. This is not a screensaver. I always need to share with people it's not a screensaver, but the Mandelbrot set is being calculated in real time. You know, you're looking at, between +1 and -2, and between plus and minus I, and this is all being calculated in real time. And it's splitting up the work into 16 chunks, so it can do it very quickly and very effectively. By the way, everything that I'm showing you today with Parallella, all the software, all the hardware, everything about Parallella is open source. So if you want to dig into this yourself, you can. If you're an electrical engineer and you want to take a look at the circuit diagrams for the Parallella, you can. You can go to github.com/Parallella, and they're right there in front of you. And the software is right there for you too. So that's one of the most exciting things about Parallella. It's open source, and as engineers and scientists, we can dig into it as well, at will. So why parallelism? Why do we care about parallelism? I'll give you a couple of examples. One example that I like is finite element analysis. And many of you who've taken some engineering course, you're familiar with finite element analysis. Say you have a component of a bridge, that rust-colored, rust-looking device in the back. Say you have that component of a bridge, and you want to know, will it break, will it wear out, and will it work? So what you do mathematically is you break it up into finite elements, into smaller pieces, and you construct a free body diagram for each piece. You know, this is from physics. The sum of all, or rather the vector sum of all of the forces on that free body will tell you whether it accelerates in one direction or another. And then by examining that, you can determine, you break it up into all your finite elements, and you can determine whether that object will fall down or stand up. And you know that in advance. And of course, structural engineers, mechanical engineers, civil engineers, they all use this because it's a great way to know what will happen in advance. And finite element analysis is an example of a problem that will work very well in parallel and works very quickly in parallel. Weather prediction is another place where this is important. Weather prediction is very important for airlines because you want to avoid, pockets of bad weather, or weather that is bad for airplanes, I should say. Because weather just is what it is, not necessarily good or bad. It just depends on what you want to do, right? Sometimes you want a hurricane if you study hurricanes, right? So then hurricanes are good. So in weather prediction, what you're doing is you're dividing up your map into cubes. And you're looking inside of each cube, you're looking at temperature, dew point, pressure, whether or not it's raining. And by looking at adjacent cubes and by looking at them within a certain time frame, you can predict what's going to happen in the next adjacent cube. And if you make your cube small enough, your predictions get better. The smaller you make your cubes, the smaller you make your rectangles or your cubes, the more accurate your prediction will be. But of course, the smaller you make those cubes, the more powerful your processor needs to be. So that's where parallelism comes into play, because then you can get more of these happening at once. Now let's talk about barriers to entry, because getting started with Parallella there are some headaches in getting started with. I know the people who run the company would want me to use the word headache and Parallella in the same word, because that's just not good marketing, is it? Well, it is. There are some headaches involved with that. One headache is that the documentation it's challenging. And there's some of us who are blogging about our experiences. I've written some blog articles about it, and some other people on the web have written blog articles about it. When I run into a gotcha, when I run into one of those problems that takes me a whole day to solve, and I look back and I say, my goodness, it should have taken me like 10 minutes, you know. Nobody else has those kinds of problems ever, right? You never run into those, okay. So when I run into those, I tend to blog about that kind of stuff as I learn more about it. And there, you know, many people in the community are doing that more and more. That's one of the ways that we're going in and removing some of the barriers to entry. One of the things that I needed to study was, we do SSH at work, but, one of the things I wanted to be able to do is do SSH and do X over SSH. And to take a look at the frame buffer over SSH, the parallelism frame buffer over SSH on my Mac. And it took a while to put a lot of that documentation together. So, I'm working on that, and some other people are working on that. I wrote an article about that a few days ago that I posted on the blog also. But one of the reasons I wanted to speak to all of you is that if you're interested in this, I would also encourage you to blog about it, because then we can share all of the knowledge that we have. Yes?
Just quick, by headless parallel, you mean it's like a version of the board that doesn't have an HDMI?
Oh yes, you know what? Yeah, when I toss it on, yeah, please, yeah. A version of the board that does not have, it doesn't have HDMI, and it doesn't have USB for the, USB for the keyboard and mouse either. Yeah, there are multiple versions of the parallels. So yes, right. And so the reason you want to run it headless is, like an example, Jeff mentioned this when he walked in here. I might want to take my parallel to a coffee shop, plug into the Ethernet port, plug that into my Mac, and just SSH into it. And who cares if I have HDMI or not? I can do, I can look at the display as if I had the display over X if I want to do that. So yeah, thank you. Yeah. Another question that some people raise is, parallel versus GPU. GPUs are parallel computers. GPUs, graphical processing units. And in fact, one of the things that I learned when I began studying Parallella and studying parallelism, I had to take a look at my Mac. Inside of your MacBook Pro, or pretty much any laptop that's sold today, I don't want to say just Mac, because any, Dell, anybody that has a video card, if you have an NVIDIA video card inside of your machine, you've got a bunch of parallel processors in there. In the case of this laptop, I didn't know, there are 384 cores in there, just devoted to video. But there's a difference between GPU cores and the general purpose cores inside of the parallel. One example, GPU cores are really designed to do one thing really, really well. In the case of graphics cores, they're especially adept at drawing triangles over and over and over again very quickly. Because if you're doing 3D pictures and shoot 'em up games or whatever, looking down the hallway, you gotta get the bad person down there with your gun and all that, because it's very, very important for it to happen quickly, right? You want your GPU to draw those triangles quickly. And here's a metaphor. If you look at robotics, GPU versus Parallella, specialized versus general, it's like having specialized, a specialized robot in an auto assembly plant that does one thing over and over again, picks up a part and assembles it with another part, versus a general robot that is programmed to play soft, for example. Yeah, you had a question.
No, actually I had more of a comment. It's not necessarily true. There are GPUs that actually are based on the same type of architecture as the GPU. The only difference is that it actually has no video port. What I'm talking about is the NVIDIA Tesla card, which basically has no GPU port. It's basically the specialization of the GPU is that it's pretty good at number crunching, nothing else.
Are you working with the NVIDIA Tesla right now? Do you have one? Are you playing with it right now?
No.
Okay, because I would love to ask you about that. That is something I've heard about the NVIDIA Tesla, and I really admire what NVIDIA is doing with GPUs and just pushing this forward. So yeah, I definitely want to ask you about that.
Yeah. And
Thank you for that.
And I also know that even the Intel also has their own version called the Intel Phi, and AMD has, I believe, Crossfire.
Are you working with them? Do you have those right now? Are you
No.
playing with those right now?
I probably could find how to get those.
Okay, okay. Because if you were personally working with those, I want to definitely dig into that with you and understand that with you. I hear about what Intel is doing and what NVIDIA is doing, and you're the kind of person that I want to just totally pepper with questions. So yeah, let's do that. Let's talk about embedded systems, because that's one of the things that I wanted to make sure that I shared with everyone at the top. Parallella, originally, when I first began playing with it, I was excited. Wow, supercomputer that you can fit in your pocket and all that. And what if we could put a bunch of them in a rack? And I mean, could we compete against Cray and all that? You know, that's what I'm thinking about. That's exciting. One of the challenges, though, is that if you want to enter into the supercomputer marketplace, there are really two players right now. There's Intel and NVIDIA, the two that you just mentioned, right? Intel is a 900-pound gorilla. You know, 90% of the processors in supercomputers are Intel processors, right? And what the Parallella team is looking at, rather than looking at the Parallella as just a standalone supercomputer, or as a supercomputer that is, or as a component in a Beowulf cluster that forms a supercomputer, one of the things that the Parallella team is looking at is using the Parallella in embedded systems. So what they've started to do is they're making it very easy for engineers and scientists to attach the Parallella to other devices. In this photograph, we've got the Parallella. There are two boards on the left. And you know what, afterwards, you can come up and take a look at this, because I have these devices here with me. On top is the Parallella. Beneath the Parallella is what's called a porcupine board that attaches to it. And here's another photograph. The porcupine board is exciting because it's got GPIO ports, general purpose input-output ports. But wait, there's more, like an infomercial, right? It's got an attachment that accommodates a Raspberry Pi camera. So you can just buy a regular Raspberry Pi camera and hook it up, and that's what we have there. In the foreground, this is a Raspberry Pi camera. You can see Raspberry Pi on the printed circuit board. It's a Raspberry Pi camera attached to the porcupine board that is attached to the Parallella. So the hardware designers at hardware designers at Parallella created this, and then they realized they didn't have drivers for it, so they created a bounty, a $4,000 bounty, for people to write drivers for the Raspberry Pi camera running on Parallella. And it's a bounty done and you can read this, the link to it. By the way, these slides are already up at rayhightower.com if you want to dig into those. But 3 of the 4 $1,000 bounties have already been claimed by one person. So there may be some people here who want to jump on that last $1,000 to help make the Raspberry Pi camera work on Parallella. And it's all open source, and the camera is only the beginning. Imagine a project that you might be working on, something involving robotics. I know some of you are involved with Pumping Station 1 or Blue 1647 or some of the other maker spaces around where people are experimenting with robotics. Maybe Parallella can be a device that could save the number of circuit boards or reduce the number of circuit boards you include in your design. So we're at the end of the talk right now. This is Parallella. I have a couple of them up here if you want to look at them directly. It's an 18-core computer. You can buy it for $99 or $149, depending on whether you want to go headless or not. You can buy it online. It's a great way to experiment with parallelism because we need to come up with a way to extract more performance out of our silicon, and parallelism might be one way. Thank you for listening. Yes?
I'm assuming somebody playing around with this is mostly interested in how fast the parallel cores are running. Like, so the operating system is loading off a micro SD card?
Yes.
Have you done any experiments to see whether the rated speed of that SD card slows up the system or not, or does that not really matter? It seems like there's a range of speeds available.
Right.
It's hard to find really fast ones.
Yes, yeah. The question is, how does the speed of the SD card factor into loading the operating system and really booting the parallel system, right? Is that essentially it? I have only used it with Class 10 SD cards because I had an experience working with SD cards years ago on another device where I was working with Class 4 and Class 10, and I hated the Class 4. So I'll never use a class 4 again. So I don't know because I'm only going to use the fastest SD cards available. So I'm sure it's a factor though, because it's like when the speed of your hard drive. If you're using a spinning mechanical hard drive, that's going to be a factor also. But I can't compare multiple SD cards because I've only used class 10 SD cards. So, but I think you're absolutely right. I think it is a factor. I
suppose a lot of people would pump the results of the calculations back out the Ethernet port for something to be stored elsewhere anyway.
Yeah, they might do that. Yeah, there's so many ways it could go. Yes, yeah. And the Ethernet, I'm glad you brought that up. The Ethernet is gigabit Ethernet too. So yes. Yes, sir.
I was noticing a lot of your demos and slides are written in C. Can you use like C++ and a lot of template programming in order to work with the Parallella?
Oh yes, the question is the examples that I showed were written in C. Can you use C++? Yes, you can use C++. You can use C. A Python interpreter comes with it. I've installed Ruby on it before. I've done that. So yeah, it will accommodate multiple languages.
What version of C++ can you use? Because there are some built-in features and potential built-in features coming up with the new C++ 17 standard that supports parallelism and kind of experiment on how that parallelism would perform onto Parallella.
Yeah, well, in other words, will it support C++ 17? Well, I guess the first question is C++ 17 really going to come out in 2017, right? Because remember C++ OX?
I think they're pretty much going on, like keeping themselves on track so far.
Okay, that's good.
I think the reason why it was that they didn't really have a roadmap and there was nothing to do. So 17 was actually, or 11 was actually a big jump.
Yes.
In scale. Once they kind of got themselves around and kind of pushed to, giving dates, because they released C++ 14 on schedule, and there's nothing really big that's going to shift the drive for C++ 17.
Yeah, you know what, to tell you the truth, I don't necessarily like to predict the future, but I'm going to do it anyway, right? What I would say is because Parallella and a lot of these other single board computers, because a lot of them are open source, we have a greater chance of seeing things come out, if not on time, then very close to on time. Because there's so many brains working on them at once. Right. It's one of the reasons why Linux is so blown up, right? Because you have brains all over the planet that are working on this stuff. And many of us who are working on this are doing it because we love it. And when you love something, you're going to devote so much time to it, and you're going to make it robust and stable. And it wouldn't surprise me if this did support C++ 17, but I will say this also. I know that the people at Adaptiva, the makers of Parallella, are also working on what's going to be next with this. Right. So who knows? Yes, sir.
Two questions, pretty general questions. I'm not a technologist, but I'm not a computer programmer here.
Yes.
The heat dissipation, the machines on the website, and I see you've got the heat sinks on sugar in there too.
Yeah.
Have you tracked and looked at the amount of heat that's generating when it's running multiple cores? The other question is around security. The application that I'm most interested in for these beyond making something to play my music is is embedded device control, and I wonder about security. I think some of the hardest attacks are coming across embedded devices that are not really very secure.
Right, right. So two questions, one about heat dissipation and the other about security. Heat dissipation, it gets hot. Now there's 5 watts going into it, and that 5 watts has to come out somewhere. It's just, what is the law for that? That's something in physics, law of conservation of energy or something like that. So 5 watts going up, 5 watts coming out, and it does get very hot. And they recommend, in fact, when I first started working with Parallella, they said, you must have a fan. They gave me this really tiny heat sink, and they said, go out and buy a fan. That's what you were working with in the early days of it. And so I went out and bought a fan, and you see that Parallella in some of the pictures on here, the one that I have with the fan. Later, they started making heat sinks available for you that are bigger heat sinks. So now, if you take a look at this heat sink, it covers all the chips on there. The actual arm and, well, I can go back in the slides. The actual arm and wrist, you see, they're actually much smaller than the board itself. And you have adhesive that attaches to the chip that says zinc on the left, the black zinc chip, and immediately to the right, the gray chip, upside down, it says additiva. You have adhesive that attaches to that, and that's what you attach to the heatsink, because that adhesive is thermal-conducting. And so that's what you're doing there. So 5 watts are going in, so 5 watts are coming out. It's got to go somewhere. And the heat sinks that you have actually are sufficient. I can actually touch this heat sink, whereas back when you had to go out and buy your own fan, you couldn't really touch that chip. So the heat sinks are effective. Second question was about security. It runs Linux, and it's running Linero, which is a variation of Ubuntu. I'd have to look at one of those. What do you call those charts? You've seen those Linux charts where they show you, in the beginning there was the first Linux created by Linus Torvalds, and then you see the descendant sub and all this, and which descendant from which one. But it's Linux, so...
it's built on the Debian Linux. If it's built on Ubuntu, then it's built on the Debian distribution.
Okay, yes, yeah. So there you go. So you can harden. I feel much more secure with that than I would feel with other OSs that are available. And I won't name them by name, but you know. You know. Yes, so yeah. I'd be very, if you do something with you mentioned that you might do something with music and controlling some other things. If you do something with that, I'd be very interested in hearing what you do. And in addition, I bet the Adaptiva would be excited about that too, because they're looking for more uses.
Well, I was also thinking as far as the security goes, it's possible that really it's also how you design in the software that you use. If you use certain softwares where you are looking at buffer overflow or underflow, that could be a potential issue that hackers can go through and kind of understand where your weak points of your security are.
Oh yeah, Heartbleed, right? That's, yeah, Heartbleed is an example. Yes, Mark.
Adaptive, that's the maker.
Yes, yes.
So when they first created this, what was their reason for making this board? Did they have an objective, or was it what?
What was the motivation? Oh wow, you're almost asking me to get inside the heads. Here's what I know in talking to the lead engineer and founder of the company. This is a guy who's passionate about chip design. And he's done chip design for several companies. He did chip design for several companies before he founded Adaptiva. And he wanted a machine like this himself. He's not a programmer. He'll tell you in a second he's not a programmer, and he'll tell you that he's not an instructor. So, some of the manuals, as he says, I'll talk, Ray, when I'm writing these manuals, sometimes I skip steps and all of this stuff. But he was motivated really by love for chip design and love for creating something that's new. And that said, I think that's one reason why you don't see a lot of applications for it yet. Some people, like, think of a Thomas Edison or something. Thomas Edison wanted a light bulb to create, light for people on time. So he was more of a practical inventor rather than someone who did research for the sake of research. So I don't know that, Zenas Andreas, also a real good guy, real smart guy. I don't know that he had a plan for applications for this, but I'm very cool that they created it. I'm very glad that they created it. Yeah. Do you have an idea about what his ideas were? Have you spoken with him? Or?
No, I was just
okay, I want to make sure I take another question. Okay, yes.
Years ago, whenever they first, that company started putting that chip out,
yeah.
They were looking at doing H.264 video compression with that. I don't know what they're actually using them for in the market, but that's what they were, a couple years back, they were looking at using it for that. And I think they have a 64 by 64 core.
Yes.
64 core chip.
Oh yeah, the 8x8,
Yeah,
yes, the Epiphany 4. And yes, the addressability of this, I'm glad you brought that up. On the address bus, there are 12 bits devoted to addressing the cores. 6 for rows and 6 for columns. If you're doing 8x8, you only need 3 bits out of those, right? In the 4x4, you only need 2 bits. 2 bits for the row, 2 bits for the column. But you've got 6x6. 2 to the 6th power is 64. 2 to the 12th power is what's that? 4,096. You can address up to 4,096 cores on this. Now, I don't know what their project plan or their product plan is, but there's potential to do that. And if they're looking at doing something with H.264 compression, I think that would be very cool. We'll see what happens with it. Did you have? Yeah.
I just had a comment. He was on the Amp Hour maybe a year or two ago when the Kickstarter was going on. The Amp
Yes.
Hour is a podcast about electronics and embedded systems, so for like a whole hour. So if people
Wow.
wanted to get more into his head, there's an interview with him on the Amp Hour.
I do want to look at that. How do I spell hand power?
The Amp Hour, like amp, like the measure of current.
Oh, amp power.
Yeah,
Okay,
amp
yes.
power, yeah.
Oh, amp and then HOUR?
Yeah.
Oh, yeah. But we need more puns in our business.
Yeah.
Okay. Amp hour. That's very cool. Yeah, you wanted to ask something?
Yeah.
I want to make sure everyone else can ask questions too.
Okay.
You're very vocal, and I think it's beautiful.
Yeah.
I want to make sure everybody else is.
Sorry,
No,
I noticed that you only, all the chips are really more RISC chips, including the ARM chips.
Yes.
But is there any plans to put more of a CIS chip, like something from Intel or from AMD?
That's a good question. Would they buy chips from Intel or AMD and mount them on this? Probably not, if only for reasons of cost. But again, that's random, wild speculation on my part. But I'm just looking at it for reasons of cost. Yes, sir.
Let's say I take this board and I actually shrink it for some boards that I have to build custom.
Yes.
How many of these chips on the board is actually required to run that library?
Oh, that's a really good question. The question is, say you have a custom application for Parallella and you like it, you have a custom application for it. How many of the chips on this board are really required if you decide to build your own circuit board, right? I don't know, but let's explore it together and let's think through some things. Now, for the Parallella functions that we talked about, there are 2. The Zen chip is really a system on a chip. There are 2 ARM cores on there, and one thing I didn't mention through this talk, there's also a field programmable gate array, an FPGA, on that Zen chip as well. So it's an entire system on a chip. You might want that depending on whether or not you want the FPGA. If you don't want it, then maybe you could go with a different system on a chip that doesn't have the FPGA and maybe reduce some of the supporting chips or reduce the size of that chip. Again, that's speculation. I think in order to do this, we would need to look at the schematics that are available on GitHub right now. But I kind of like this speculation, so let's speculate some more. And then the Adaptiva chip to the right, the gray chip to the right with Adaptiva upside down, you would certainly need that because that's where your 16 RISC cores are. However, versions of this board, like the version of the board that's the 64 core version, I think that the case, what do you call it? The case, the package for the chip? I think the package for the chip is about the same size, even though it has 64 cores, 8x8 instead of 4x4. So those, I think, would certainly be the minimum that you need, but then reduce your chipset even further. Don't put USB on there, all right? That eliminates a chip. Don't put HDMI on there, because I assume you're going to go in there headless if it's for a custom system that you're doing. Yeah, the bottom line is I think you can definitely reduce the chip count that's on there. I don't know exactly which ones you can remove, but just based on this, simple speculation we just engaged in, yeah, I think there's potential for that. And one thing I would say is, if you have, are you building something right now where
I'm just playing this.
you're playing with stuff? Okay. The founder of the company is very accessible, like on Twitter and via email. And if you have something that you wanted to talk about, I wouldn't mind doing an introduction. And you might not even need me for an introduction. If you reach out to him, his handle on Twitter is @Adaptiva. If you reach out to him on Twitter and maybe send a link to something that you're working on, I'm sure he'd want to engage you. Listen to me. Andreas, I'm telling everybody that you have free time to talk to random people. That's not nice. Yes, sir?
I would have thought that parallel would be faster than the Mac. Why is the Mac fast?
It has a
It's a
bigger.
faster processor.
Yeah.
Just a faster processor?
It's running at a faster clock speed, and there's some differences in the system architecture also.
And it also has higher, it probably also has higher voltage, so it has, it has higher wattage uses so that it can run faster, whereas you're using the parallel, which has a lower wattage, which that means that it's going to run slower.
Yeah, we should explore that. I don't want to take up a lot of your time where it's like 7:30 right now. I want to respect your time. How are we okay?
Yeah, we at the far end, we typically go as much as 8 o'clock.
Okay. Is this good?
This is good too. People probably want to come up and see these up close.
Yes. If you would like to come up and see these up close, you can. Thank you so much for having me.